We now continue with properties of cross product. So this is the equation that we established in class last time, which defines the magnitude of a cross product between two vectors that are in an angle of sine theta between them. So today I want to start by looking into some geometrical meaning of this expression. So let's think about the following picture. We have a vector A, then another vector B. The angle between these two is going to be theta. And when we discussed the dot product, then we did the following calculation. This segment on which vector B projects onto the direction of the vector A, the length of the segment we called component of B onto A. So we denoted it by comp B on A, and that was B times cosine theta. And we showed that that's the same thing as A dot B divided by the magnitude of A. So now I want to concentrate on the other side in this right triangle. So the vertical side. In this right triangle with a hypotenuse that has length B, this side is the opposite side, so its length should be magnitude of B times sine theta. And so now I'm going to complete this geometrical figure by drawing two more copies of vectors A and B. And let me fix that. And so what this gives you is a parallelogram, right? So two sides of length B, two sides of length A. And let's say I want to compute the area of this parallelogram. And as usual, the area is going to be the length of the base times the height. The base in this case has a length of magnitude of A, and the height is this vertical, is the length of the vertical segment that I have just found. So area is equal to magnitude of A, length of the base, times the height, length of B sine theta. And of course, that is exactly the same thing as a magnitude of a cross product between A and B. So that is one version of a geometrical interpretation of magnitude of A cross B. Now, another thing that I can do is to connect the endpoints of B and A like so. And then what I'm getting in this case is going to be a triangle. So let's outline the triangle that I'm talking about. And this triangle is formed by vectors A and B. And clearly its area is going to be half of the area of a parallelogram. Or it is the length of the base of a triangle, which is magnitude of A, times the height, which is magnitude of B sine theta. So area of the triangle formed by two vectors A and B is area is equal to 1/2 magnitude of A cross B. So that shouldn't be that complicated. So now, if we do want to find the area of a triangle, we know what to do. So let's do an example. Given a triangle with vertices at the following point P with coordinates -1, 1, 1, Q with coordinate 1, -1, 1, and R with the coordinate 1, 1, -1. What I want to do is find the area of the triangle. And you can begin with a picture. And let's say we have our arbitrary 3 points. You connect the 3 points in the space, and you end up with a triangle. So maybe this is P, Q, and R. I can draw position vectors for, let's say, R and P. Then components of a position vector for R would be the same as coordinates of R. Components for the position vector of P are coordinates of the point P. And so then if I want to find the vector from P to R, it would be enough to, so let's call it PR. It is enough to take a position vector for R and from it subtract the position vector for P. So 1, 1, -1, minus, -1, 1, 1. So that's a vector 2, 0, -2. In a similar vein, I can take a position vector to Q and subtract the position vector for Q, position vector from P from position vector from Q. That will give me a vector PQ, 1, -1, 1, -1, 1, 1. So that is 2 again, then -2, and then 0, right? So I got my PQ and PR, and now if I take their cross product, compute the magnitude, and divide by 2, I'm done. So cross product of P and Q is I, J, K, not P and Q, but PR and PQ. So that's 2, 0, -2, 2, -2, 0. So that would be a vector with components -4, -4, and then minus 4 again. And so the area of my triangle is therefore magnitude of minus 4, minus 4, minus 4 divided by 2, because this is a triangle and not a parallelogram. And so this is 1/2 square root of 16 plus 16 plus 16. And so that would be square root of 3, actually, I think. Let's see. So square root of 16 comes out as 4. So divided by 2, 2. And what remains is square root of 3. And so this gives us the area of a triangle without any difficulty. Okay, then let's look at a similar question in 3D. Let's suppose that I have now 3 vectors. Vectors like this, like that, and like that. So remember what I did for the parallelogram. I drew 2 copies of A, 2 copies of B, and that formed the parallelogram. I can take multiple copies of each of these vectors to complete this picture to be a box. So something like that, something like this. Then actually we can do it this way. Another vector like that from here, another vector from here, another there, and then so one more, and then to complete one more here and one more there. And so you end up with a box, and this box has vectors A, B, and C as its sides, right? So if I highlight this one, and that. So I can ask an analogous question to what I asked about the parallelogram. So what is the volume of this solid figure? And its name, because it's formed by parallel lines, is parallelipiped. And so the question is, what is the volume of this figure? And again, it's easy to do, similar to what like you do it for rectangular box. Volume is equal to the area of the base times the height. Okay. In this case, the base is formed by vector A and B, and the base is actually a parallelogram. So this should be equal to magnitude of A cross B, area of the base, times the height. And what is the height? I can drop a perpendicular So we can drop a perpendicular onto xy plane, then project magnitude of C on that perpendicular, and that will give us a height. And so if the angle between the line perpendicular to vectors A and B, and the angle C is theta, then the height should be magnitude of C times cosine theta, because the height of the parallelepiped, right, is the same thing as an adjacent side to the hypotenuse with a magnitude length C. And then if I think about that, so the direction of A cross B is perpendicular to A and B. And so the direction from which I'm measuring theta, that direction actually is the direction of a cross product, because A cross B points in a direction perpendicular to both of them. And so that means that I can rewrite this just as A C dot A cross B. And now, remembering cycle permutations that we discussed, I can also shift C, A, and B if I wish. So, for example, I can write this as A dot B cross C. Etc. And so then the volume of the parallelepiped is going to be, as a mixed triple product, this is a determinant of numbers which are components of your vectors. And in this case, I have 3 by 3 many coordinates, and so I can form a 3 by 3 matrix out of them. So as an example, let's do a specific example. Actually, a couple of specific examples. Suppose number one, that I want to find, let me see, yep, find the volume of the parallelepiped formed by the following vectors: -1, 1, 0, -2, 0, 1, and 0, 1, 3. And so this is trivial in the sense that it's very easy to set up. So the volume is One thing that I forgot to mention that in this case, as you remember, if I interchange two rows, then the sign of the determinant will switch to the opposite. So in principle, the number that I'm computing here can be positive or negative, but it's going to be exactly the same no matter how I place this in which order. I'll place the rows A, B, and C. The outcome is always going to be a plus or a minus of the same number. So to get rid of a minus, we always take the absolute value sign. And so the volume here is the absolute value sign of a determinant formed by -1, 1, 0, -2, 0, 1, 0, 1, 3. So that, and then you take a magnitude. So this should not be very difficult, I hope. So it's -1 times cross out row in a column that contain -1. So it's 0 times 3 -1. So -1 times -1 plus 1. Actually, I'm not sure what I was doing there. So -1. Yeah, no, that's right. So plus the second row plus 1, but because it's the second element in the first row. Because the second element in the first row, you put minus in front. So then the second element gets up. And then times, you cross out the second column in the first row, and you have the determinant of -2, 3 on one diagonal, 0, 1 on another diagonal. So this should be -6 for my second guy. And the third guy is 0 times something. I don't really care about something because I'm multiplying by 0. And finish absolute value. And so what this is, then absolute value of +1 plus 6, absolute value of 7. So volume is 7. All right. So the next subject that I'm going to cover will be equations for lines. And here I would like to answer a question similar to what was asked in 2 dimensions. So for instance, if P and Q are 2 points in 2D, well, let's do 3D, are 2 points in 3D, and I want to find the equation for the line L. Right, so that's one question that I might ask myself, how to find equation for the line L that passes through P and Q. Another way to ask this question, let's say given a point P, and the line, let's call it M, find the equation of a line that passes through P in the direction of the line M. Or there is a third way that actually would be easier to formalize, given point P, in 3D. And so in addition to point, in order to specify a line, I need to also specify a direction. Direction can be specified by a vector. Actually, let's give P specific components. Let's call them x0, y0, z0. So in addition to point, if I want to describe direction, then a vector will be a reasonable thing to choose. So say along with a vector v, and this one with components a, b, c. I want to find the equation of the line that passes through P in the direction of V. Okay, now let's see how we can approach this problem. I'll do a quick picture. Let's say I have a line. On that line, there is a point P0. This is a point P, right, with coordinates x0, y0, z0. And I can then introduce a position vector towards P, and this vector will have components x0, y0, z0, and this would be my V. Now, so will be something that I'm going to call R0, right? So R0 is this vector here. Likewise, I can pick another point on the line L, and this would be a generic point with coordinates x, y, and z. And the corresponding position vector, actually, let's write this as a position vector. And this guy I will denote by R. Okay, so what does this tell me? If I now plot a vector v, right, so vector v must be pointing in the direction of my line, so v is a vector along the line. Now, if I also subtract, so this was R, R0 from R, then that will be the green vector. And we can see here is that two vectors, r minus r0 and v, are actually parallel. Okay, and if the two vectors are parallel, then they must be scalar multiples of each other. So the conclusion that we draw from this observation is this, that r minus r0 is parallel to v, and this is the same thing as saying r minus r0 is equal to t v. T is an arbitrary real number. And I hope that this sort of makes sense, because I can rewrite this also in the following way: r equal to r0 plus t times v. And then this equation should be fairly easy to recognize, because if I think of r0 as being some position in space, and that v is kind of like a constant velocity, then what this equation tells me is that if I want to figure out my position at a time t, if I'm the one who travels along this line, then to get current position, I need to take my original position, which is r0, and to that I need to add velocity times time. So this is a totally reasonable equation. So this is called the vector equation of the line. Okay, now we can take that equation and split it into components. So x, y, z must be equal to r0, which is x0 or y0, z0, plus t times v, and v was a bc. So combining this, x is equal to x0 plus ta, y is equal to y0 plus tb, and z is equal to z0 plus tc. Something like this is called a parametric equation of the curve. Notice that in this equation, this is not like a situation in 2D where equation of a line connected to different coordinates. In this case, you have four variables, x, y, z, and t. So what you can attempt to do is to get rid of t, and you'll get equations that does not involve time. And let's see what we can do. So I can solve first equation for t. T is x minus x0 divided by a. I can say I'll solve the second equation for t. That's t equal to y minus y0 over b. And I can do the same thing for the third equation. So T is Z minus Z0 over C. And now you see that all of these three T's must be exactly the same T. So we conclude that for X to be on the line, it must satisfy this equation, X minus X0 divided by A equal to Y minus Y0 divided by B plus is equal to Z minus Z0 over C. This equation does not have a parameter present anymore. We eliminated it. And that would be now a symmetric equation of a line. So we have these three options to define a line. Examples. Let's say, yeah, I have 2 points. Let's say 1, 1, and 2, 3, 0. I want to find the equation of the line that passes through, let's say, let's call this P and this one Q, passes through P. And so really, this is not a very complicated story again, because for an equation of a line, I need to simply figure out what the vector in my direction is and what the point that I want to pass through. Okay, so given that P and Q both should belong to the line, right? Then the vector P, Q minus P, the difference between the position vectors, must be in the direction of the line. So I can take P equal to P0. Then I need to find the vector which I didn't give you, but maybe I did. Let's see. So I have 3 points. So not 3 points, I have 2 points, right? 2 points P and Q. So I can find the vector from P to Q. And then I need a line that passes through P and Q. So this line must be parallel to PQ. Take a position vector, subtract the position vector. So PQ, in this case, components of position vector for Q2, 3, 0, minus components of vector of the point, coordinates of the point P. So minus 1, 1, 1. And so this would be 3, 2, minus 1. And so now I know P, I know Q. So my vector equation of a line is going to be x, y, z equals to position vector for the point P, which is minus 1, 1, 1, plus t times the vector in the direction of a line, and that's PQ. So and so let's see. So it's minus 1, 1, 1 plus t 3, 2, minus 1. And so then a parametric equation of a line will look like x equal to minus 1 plus 3t, y is equal to 1 plus 2t, and then finally z is is 1 minus t. So these are your parametric equations of the line. And then finally, by eliminating t, I can get symmetric equations. So I need to eliminate t. From the first equation, t is x plus 1 over 3. From the second equation, it's y minus 1 over 2. And from the last equation, z minus, or 1 minus z is t, right? So this is just 1 minus z. And that is your equation of a line in 3D. Okay, so next time we're going to discuss this in further details.